Okie dokie. So last time we talked about signaling interfaces and PSTN signaling for, as kind of the same way we talked about SIP, and learned that we are using interfaces that Graham Bell would recognize up through things that were invented not terribly long ago, at least around my time I was born. I don't consider that terribly long ago. And SIP, of course, has come in the last 15 years at the most. It kind of depends on where you want to drive a nail is when SIP started. It's actually been adopted heavily in about the last 10 years or less. There are a ton of PSTN connections out there. If you look hard enough, you can probably find a little bit of everything. We're going to whittle this way down to two interfaces that you are likely to see. They're the ones we've talked about. There's a single analog connection that you mostly see, which is that loop start that we talked about last time, where you have voltages and currents flowing and all that sort of thing. And the most common digital connection for the PSTN is something called a T1. You've probably heard of that in terms of data connections. T1 was actually designed originally to move voice. We're going to look at it from that point of view today. We're actually going to study it more later as a data connection and kind of see how we got from A to B. The big thing today is I want you to see I had to find a place to put how these things work. This used to be about a third of the class. We're going to spend probably a day and a half on it. So that's how fast these things are changing. When we talked about the analog signaling last time, if you'll recall, we mentioned that in the kind of signaling we were looking at, there were 4 states. Anybody remember what they were? What's the quiescent state? The state that when a phone's waiting. On hook. Okay. What else do we have? Off hook is what? Describe to me in terms of that local loop. What's happening in off hook? I'm sorry? Starting to make a call. How does the switch know something's happened? Circuit is closed, which means we're drawing current. Right. So we move from this point to where the phone is off hook. So I've picked up the handset. That circuit is physically closed. We're drawing current. The switch detects that current flow. Since you're the one that made the change and the switch didn't send you anything, it knows that you're trying to do something, make a call, so it's going to send you a progress tone. What's a progress tone? It's called dial tone. There are a lot of progress tones in this system. Dial tone is one that says the switch is ready for digits. It actually used to be a big deal to wait for dial tone, and at least in my lifetime, you've rarely had to wait for dial tone. So anymore, it's just kind of something that happens. So I'm the switch. I send you dial tone, and basically what I'm saying is I need digits. So you signal digits to me either by push button, or if you have a really old phone, I couldn't help myself to put rotary phones on this one. You run your finger through and open and close that loop, basically to count up, but we're not going to worry about the details of how that happens. Basically, you provide digits to the switch. You say, here's the address that we want to go to. All of that is still off hook. Okay? From the status of that connection, even during dialing, that connection is off hook. That's its state. It's not in a call, but it's not on hook. So we're in kind of an in-between state. It's not ringing because the switch is not sending ringing voltage to it. Okay? But when I provide digits to the switch will interpret them, assuming the other endpoint, this is a simple call, assuming the other endpoint's on that same switch, the switch will go to the port that is specified by that address, and it's got to let you know there's something there, so it's going to send ringing voltage. That's that alerting voltage that rings the bell. The way the circuit is set up, it can actually send ringing voltage to you even though the loop is open. If you're interested in the hows of that, I'll be glad to tell you. I don't go into it in depth in here anymore. When you So at that point, what's the state of the phone you're calling? Is it on hook? Hadn't been picked up yet. It's in its own state called ringing. On hook means it's quiescent. You know, it's waiting for a call. Off hook means I have initiated. I've picked up the phone and I've initiated something to the switch. Ringing is when the switch is initiating and sending that ringing voltage to the phone. The phone is no longer on hook because it's got ringing voltage going to it, but it's not off hook because you haven't picked it up. So, in other words, we've got a third state. That's that ringing one. Typically, a switch will not deliver another ringing state to it. You can kind of come up with some weird situations where you would, but normally, if a phone is ringing, it's not available for another incoming call. A second incoming call would get it busy. Okay. Assuming you don't check your caller ID and you pick up the phone when it's me calling, then you've changed your state and you're the one that's changed it, right? The switch was sending you ringing voltage. When you pick up the phone, what happens? It completes the connection, but from a signaling point of view, what happens? I was sending ringing voltage to you. You picked up the phone. What happened on that loop? You close the loop, so what happens? What happened on the other one when you close the loop? You drew current. Same thing's going to happen here. You pick up the phone, it's going to draw current. The switch will detect that current draw and say, oh, you've answered the phone, so it removes the ringing voltage and sends the audio through. Now we've got both phones off hook. And if you look at using that same little signaling diagram like we use for SIP, you can actually chart this whole thing out. You know, we'll draw, in point starts the call, it draws current, sends that to the switch. The signaling exchanges, the switch sends dial tone, you send digits back. The switch sends ring voltage to the endpoint. You answer the phone, draw current. The switch removes the dial tone from, actually I should have put remove dial tone before, I'm sorry, that's supposed to be up at the top. Removes the ring voltage over here and cuts our audio through. When one of us hangs up, that end stops drawing current, which signals the switch, this call is over, and it drops everything. Okay. I'll fix the remove dial tone. That's pretty much it. There are a couple of terms you need to know on this. First off, a warning, there are just of this. This is what we called that loop start. There are actually 3 or 4 variations on this. They're mostly under the hood. They mostly have to do with that answer supervision that I told you about where I can control your line. That's what most of the variations are. There are other analog signaling methods out there. Haven't seen them being installed for new links, so we're not even really covering them in here, but you may run into them. They all do similar things. They put a voltage across the line, they draw current, they do something to show, to do this same sort of signaling. The ones you may hear about are E&M, ear and mouth, or earth and magnet, depending on which end of the argument where that term came from you want to. It's actually 2 control leads, one named E, one named M. Everybody made up names for them. And there are 8 variations on E&M signaling. There is something called ground start signaling, which was actually designed as a trunk. Loop signaling was not designed as a trunk. It was designed for a line. But it's cheap. So we use it. So anyway, we're going to limit our discussion to analog loop start. When you're dealing with that, you're going to run into the terms that you see on your digital devices. One of them is the FXO interface. Now this is one of those confusing things. FXO stands for Foreign Exchange Office. By definition, an FXO interface draws current and receives ring voltage. Okay, what is it? It's a telephone interface. If I string another switch out and make a trunk, it's the end that acts like a telephone. Okay? The other end of that link, and they form a mirror image signaling system. Each end does different things, but those different things match up exactly. The other end is called FXS, Foreign Exchange Station. An FXS interface provides current and sends ringing voltage. Okay? There are actually a couple of other things they do, but for our purposes, that'll suffice. So you can see, what does an FXO interface do? It chimes. What does an FXO interface do? It does two things. It draws current and receives ringing voltage. Okay? What happens if I put two FXO interfaces talking to each other? They're both trying to draw current. Nobody's providing current. It ain't going to work. They're both trying to receive ring voltage. Nobody's sending ringing voltage. It ain't going to work. Similarly, if I put two FXS interfaces together, now we got the opposite problem. Everybody's trying to provide current and everybody's trying to provide ringing voltage. Again, it ain't going to work. FXO and FXS are the $5 term is symmetrical signaling pair. Each end has its own specific functions, and they match up exactly with the other end. You must implement these FXS on one end, FXO on the other. Okay. Now, where do the terms come from? They come out of that old PSTN hierarchy. Remember, you had local switches at the bottom that connected to users, and you had trunks going up. At the local switch level, this is pretty easy to see. The phone's the FXS. Switch, I'm sorry, I said it backwards right then. The phone has the FXO on it. The switch has the FXS. Everything's cool. What happens when we move up and we have a switch talking to another switch? Which one there? At that point, honestly, from a signaling point of view, it's arbitrary. You could pick either end to be it. The way it was done in the hierarchy is the higher level switch had the FXS interface, the lower level switch had the FXO. And if you think about if we tilted it so those phones were downhill from the switch here and signaling flowed downhill, then it would make sense about the orientation. I'm sorry?
FXS sends current, does it also send the ringing voltage?
FXS draws current, doesn't send current. I'm sorry, I said that backwards. Like I said, it's confusing. FXS provides current. You're absolutely right.
Does it also provide the ringing voltage?
Yes, it provides current. It provides ringing voltage. FXO draws current, sinks current's the term, and receives ringing voltage. These you still see, and this is probably the most confusing thing for people who are new to implementing voice over IP, because you get a little interface card. You'll see them in your lab system in here, and they're labeled FXS and FXO. Oh, great. What do we use? If you connect them incorrectly, it's never going to work because the signaling won't point correctly. Usually you buy them in multiples of 4, and you can buy them in just about any combination. So you actually have 16 variations on this stupid card you plug into your router. It gets confusing. What you're looking at, and we'll look at traffic engineering towards the end of the semester, but basically you buy on your router, you're making your router on this connection look like a phone. So which interface am I going to put on the router? FXO, exactly right, because I want that to look like a phone to the switch on the other end in the PSTN, which is an FXS. Okay? If you have trouble keeping them straight, and I obviously flip these around, I want to get my mouth going. S connects to a station, so the switch has FXS on it because that's connected to a station. O connects to an office. So for my router, I want to connect to an office. Therefore, I put an FXO interface on. Okay. that's the analog world as far as this class goes. We'll implement these in the lab. You'll see them work. If you run into the other variations, basically you're still buying an analog interface that's going to match what's on the switch, and you're still going to program it and dial plan it the same way. You just buy a different interface. This is by far the most common. Yes, sir?
In those systems where they have the kind of have their own phone system inside the corporation, they have an FXO on the outside and an FXS on the inside.
That's exactly what they have. The other number to kind of keep in mind in terms of connections. I mentioned State Farm the other day. Typically, a local agent will have 2 to 4 analog connections out of that office, to get to the LEC. You need analog for fax machines, and insurance is one of the industries that still uses fax. The way the economics of it work, if you're going to buy analog service, it makes sense to buy individual lines, 4 FXO connections or what have you, up to 4 or 5 lines. Kind of depends on exactly where in the country you're standing. But above that, it's more cost effective to go with the digital route, the T1 based route, which we're going to look at here in a minute, a PRI. So you see analog connections for 2 reasons. One are small systems that need a little bit of local connectivity. The other one is the everything else is broken connection. My digital stuff's gone down, my ISP's gone down, but my analog, my 2 or 3 analog connections off this site still work. And in most places, CSI has it. You walk over to our phone room, surrounded by all the racks of internet gear and all that stuff, and what you'll find on the wall is an analog telephone directly connected to get off campus so that we can, in fact, call off campus if you need. That's still pretty common. Okay, that's the analog world. It is much larger than this. This is the one you're likely to run into. Okay. For the rest of the day, we're going to talk about the rest of this. If you'll remember, when we were talking about signaling, we talked about a device called a codec, which took an analog signal in, coded it, sent it across a digital network. That's what the rest of this presentation is. Specifically, we're going to look at what is called the TDM, time domain multiplexing hierarchy. You've probably heard it called the T1 hierarchy or T1 family. You may have heard it called the DS1 family. We'll get into all those terms a little bit. The very first level of that is what we do with an individual single voice line. And we talked about this a little bit the other day. I didn't actually dig into exactly what's going on. I take one voice signal, analog input. Back at the beginning of the semester, we talked about the characteristics of telephone analog audio. And what we came up with is that we had to pass 300 hertz, 300 cycles a second, which is a fairly low tone in your voice. I can probably force my voice down to 300 hertz if I really try. Through 3,300 hertz, which is pretty high. It's not the very highest that the human voice can make, but it's way on up there. Almost all of the intelligence, the absolutely mandatory audio is in that range. Now, the stuff that makes it sound pleasing for, music and things like that are outside that range. But we can pass the information in a spoken word in that range of 300 to 3,300, which, if you do the math, is a bandwidth of 3 kilohertz. Okay? In the analog days, we did all of this with filtering. Okay? And so what they did was actually filter the system. Because filters don't work perfectly, you can't say, I want 300 hertz to be the cutoff and 299 hertz doesn't get through and 300 hertz does. We can do that with digital techniques. You can't do it in analog techniques, which is how all this stuff was built. So we actually built the filters a little wider than we needed them to be. We actually let the filters pass 0 hertz through 4,000 hertz. So here's a 4 kilohertz channel with this 3 kilohertz signal in the middle of it. Okay? The extra bandwidth is called guard band. Now in our digital world, why are we worried about that? Remember the concept of magic numbers? Those are those things that kind of echo through because everything's been designed based on what was there before, based on what was there before, based on what was there before. That's what we've got. From the analog days when that channel was 0 to 4 kilohertz, that was the channel when we started doing coding that we based all our numbers on. Okay, this is 1958 when we're doing this kind of technology. With that in mind, there were two numbers we came up with. Bell Labs literally sat people down in a lab and they sampled audio at various sample depths, 3 bits, 4-bit sampling, 5-bit samples, 8, 12, I think they stopped at 12. Anyway, they literally sampled it that way and then played it back to people. Which one sounds best? They were going for what was called toll quality audio. This is local. Remember, long distance added noise and was predictably adding noise. So they wanted local quality across this kind of link. Okay? My point in telling the whole story is that it was an empirical measure. There's no magic number behind it. It was empirically they determined that with the technology available to them, they needed to do 8 bits. We'll come back to that when we look at voice over IP protocols. So we know that every time we sample this waveform, you remember sampling, we're going to take an analog waveform, we're just going to look at it periodically, and we're going to measure some aspect of it. In this case, we're going to measure the amplitude. When I measure that, I'm going to measure it to an accuracy of 8 bits, which means I've got 256 possible levels, right? 0 through 255 is the number of combinations you can make with 8 bits. Now, there's a very smart fella named Nyquist, and he got to looking at this whole idea of sampling. He actually did this in the 30s, before anybody could even really do it. He got to looking at it. And he came up with a rule, and we call it, of course, the Nyquist rule, that to unambiguously sample an analog waveform, in other words, to come up with a set of samples over time that only describe one waveform, you have to sample that the input audio at a minimum of twice the highest frequency that's going to come through that system. Okay? Here's where our magic number comes from. All of our network had been built on passing 0 to 4 kilohertz. Okay, so what's the highest frequency that could possibly come through that system? 4 kilohertz, right? We know that we weren't even using that. We were passing a maximum of about 3,300 hertz. There were some other reasons we needed stuff in there, so we'll leave it at 0 to 4 kilohertz. Nyquist said you have to sample that at a minimum of twice that rate. So 2 times 4,000 hertz means we have to sample this at a minimum of 8,000 samples a second. Okay? 8,000 samples a second. Every sample has 8 bits. We have to move 64,000 bits a second to code the human voice to the quality they wanted to do in that case. Today, we can do it with 3 or 4 bits. We do it with a variable number of bits. We're a lot better at doing this. But this is the number we live with, and this is, in fact, still the method used on the public switch telephone network. And this coding algorithm is used in voice over IP. If you've ever set up Skype or something and selected G.711, G.711 is this coding encapsulated in a packet frame instead of sent to a T1. That's all it is. Okay. You okay with this? I mentioned this is the first level. And when we talked about digital transmission, I said that the phone company never actually intended to use digital transmission for the connection to the phone. It happened later, but not because they designed it that way. They sort of caught up with it later on. This was the first step in doing multiplexing. So this signal, this 64 kilobit signal that is a single coded voice channel, is known as a DS0 or DSO. Okay? Digital signal rate 0. What's the 0 mean? level of multiplexing. Now, I've talked to some of the folks. I was fortunate enough to meet some of the folks who were working on this in the 50s, and they're just fascinating. They're funny. They were funny guys. And I heard 3 different grand explanations of why they used DS0. And I didn't believe any of them. I think they forgot. I really do. And so when they started doing hierarchy, they thought, okay, our first hierarchy is going to be DS1. That's going to be this, this, and this. I think they forgot a name for this. I truly do. In the for what it's worth category. So now, what we have, we've taken an analog audio signal that matches what's moving on the public switch network. We have coded it to a digital form that we can send across a digital transmission system. We've defined a rate for that, 64 kilobits, and we've given it a name, DS0. This is the voice equivalent data rate. So everything I'm going to do in this system that's going to move the human voice, I'm going to do in a multiple of 64 kilobits because that's a voice channel. Remember, we're not doing data with this. This is voice. It's 1959, 1960. Internet's still about 8 years in the future. Once we get our sample, you saw this one the other day. Once we get our sample, we take our bits, we stick them, we code it, we send them across the link serially, we reconstruct that sample at the other end, and then we use an integrating circuit and turn it back into analog audio. We do that process that I just showed you 8,000 times a second. So we have to run that link in the middle 64 kilobits. Since we're wanting to multiplex, what we're going to do is take one 8-bit sample from each of several channels and send it across the same link. We're just going to stack them up in order. So channel 1 sends 8 bits, channel 2 sends 8 bits, channel 3 sends 8 bits, so on and so forth. When we get to the end in this case is actually channel 24. We'll send 8 bits in channel 24, then we run back around and we start with channel 1 again. And if you go through the math, 64 kilobits times 24 channels is 1.536 megabits, or 1536 kilobits, whichever way you prefer to see it. The problem with that, if you think about what the receiving end has to do to find its sample, all it's got to do is count, right? First channel gets the first 8 bits, second channel gets the second 8 bits, so on and so forth. How do I know where to start counting? You see the problem? We turn on one end, it starts coding audio. This is synchronous. It doesn't start and stop. It's doing this continuously. We're not sending packets. There is no packet structure in this. We do, however, have to have a way to let the receiving end kind of know where it is in this whole stream, because you can't predict which end's going to come up first. And we want it to be able to do it fairly quickly. So what we're going to do is work on this a little bit. And we're going to add a little bit of bandwidth. We don't want to give away. The more control functions we build into bandwidth, the less of this structure we can use to make money. Okay, remember that's what they're doing, is selling this access. So we want to be real careful not to just tack on data to this all along. We're going to define a frame. We're actually at layer 2 now. Remember that the difference between layer 1 understands what data, what amount of data does layer 1 understand? Yeah, layer 1 is a single bit. Layer 1's job is to determine whether that bit is a 0 or a 1. That's it. It doesn't interpret it. It doesn't assign meaning to it. It just says whether it's a 0 or a 1. For those bits to have meaning, we have to build some structure around them. That's what layer 2 does. Layer 2 defines frames. You've heard this term, Ethernet frames, all of that. When you looked at Ethernet frames, how did you know that a particular bit had a particular meaning? What told you what the meaning of a particular bit was? Okay, and the header was what? When you had an Ethernet frame, what you had was just a series of bits. An Ethernet frame tells you exactly how many bits are what. And it will define bits 1 through 4 do this, bits 5 through 7, and I haven't looked at Ethernet in so long I can't remember what they are. But you know, different pieces of that have different numbers of bits to define what's going on. That's what a frame is. It's a structure that we build to impart information, and then later one fills in the bit values for a given frame. That's what we're doing here. What I'm going to do is impose a framing structure on this. I'm going to insert a framing bit as the first thing I send out the door. So I'm going to set a framing bit, then the next 8 bits, so bits 2 through 9 of that frame are the 8 bits from channel 1. Bits 10 through 10, 11, 12, 13, 14, 10 through 17, right? I think, 16. 10 through 17 are channel 2. The next 8 bits are channel 3. How does it help? Because what I'm going to do over time is make this framing bit absolutely unmistakable as to what it is. And what I'm going to do, we'll get to how we do it here in a second. Notice what we've done. We're putting one framing bit on the front of every one of those sets of samples. How many samples per channel do we have in a second? 8 bits times 24 channels. How many bits do we have per sample in our DS0? Each sample consists of 8 bits. Yeah, remember? We sample at 8 bits. So what we're doing in this scheme is we are taking the 8 bits from each channel, stacking them together and making a frame. That's 192 bits. We're adding a bit on the front of that, called a framing bit. How many times a second am I going to do this? There you go. Remember that to move 1 channel's worth of audio, I have to move an 8-bit sample every 8,000th of a second. So I'm going to move this entire aggregate frame every 8,000th of a second. Okay? Which means 1 framing bit, 8,000 frames a second, I've added 8 kilobits to this data stream. So if you go through the math, I've got my samples, 24 channels, times 64 kilobits. There's my 1.536. I add 8 kilobits of framing, so I know where I am in this whole structure. And we end up with a data rate of 1.544. If you go look up T1 or DS1, that's the data rate. You okay with this so far? Just keep in mind the steps. We code audio to 8 bits. Nyquist says we have to send 8,000 of those samples every second, so that's 64 kilobits. We do it by sending an 8-bit sample from each channel of 24 channels across a link, and then we mark it with a framing bit. Okay. Now we can actually do this in multiple levels. Pretty much everybody's heard of a T1 or a DS1. That's a fairly common data rate that you see. The digital multiplex hierarchy actually has a bunch of levels. DS0 we talked about, that's a single voice channel. DS1, why are we saying DS instead of T? Hold that thought. DS1 is 24 DS0s multiplexed together with framing added. Okay? A DS1C is two DS1s multiplexed together with a little bit of framing added. You can go on down the list. DS2, DS3. DS3 is one you've probably heard of. If you've heard of a T3, for example, they're out there. T3 is 28 DS1s multiplexed together with framing added. And it goes on up. You can see the rates. The ones that you actually see out in the world are DS1. You might see a DS1C. You see them a little bit in big cities. You'll never see a DS2 by itself. They were used inside switches. DS3 you'll see, DS4 is a carrier rate, DS5 is a carrier rate. But DS3 was usually the largest that was ever sold to a customer. I'm not worried about you memorizing these numbers. I want you to realize this is a hierarchy. And what we're doing at each level of this, once you go from DS0 and take 24 of those and make a DS1, all the rest of this is exactly the same process. You change the numbers. So I take a frame from each DS1, add some framing to it, and I make a DS1C. And I go on up the hierarchy that way. Actually, I think I want to stop here. No, man, we'll go on. Okay. So what's the difference in a DS1 and a T1? A DS1 is a data rate, or DS2, or DS3, or DS0. All you're describing is how fast data moves, period. The carrier designations, T1, T1C, T2, T3, all that stuff, what you're saying is this is a DS1 on this particular physical interface. In the case of a T1, you are taking a DS1 signal and putting it on an interface that consists of two copper twisted wire pairs. Okay? As you go on up the hierarchy, these have different physical implementations. It's kind of like if I say I'm going 70 miles an hour, that's kind of what DS1 says. If I say I'm going 70 miles an hour in a Ferrari, that's like a T1. I've given you more information. Okay. T1 tells you rate and interface. DS tells you rate only. Okay. Okay. So realize where we are, take a breath, and we're going to look at one more little piece here. We have moved from an analog audio signal, coded it, and figured out a way to move a lot of those voice channels over a multiplex channel. Why would we do that? Remember that we had two goals that we were going to try to address. One was noise and attenuation, right? Analog circuits inherently have attenuation involved in them. You inject a signal into a copper media. Some of that energy goes into heating the wire sooner or later, meaning as you move further and further and further down a wire, that signal gets to the point where you can't detect it. There's not enough power there to differentiate it from the noise, which brings the second issue up, noise pickup. To overcome that distance limitation, I need to amplify that analog signal. When I do that, as we looked a few times ago, you amplify not only the original signal, but also all of the noise it picked up along the way. Over several cycles of that, the noise level builds up while the signal stays the same. So you've degraded the signal. That's why I said they were wanting toll quality audio when they looked at their sample rates. Okay, so all of this ties back to that. So we've actually addressed that part of the problem simply by going to digital transmission. We code audio. Coded audio isn't immune from attenuation, but it makes it easier to detect at the end. You're not detecting subtle variations in the analog signal. You're trying to tell whether a particular pulse is a 1 or a 0. Well, if I set those pulses sufficiently far apart, 0 volts and 10 volts, pretty easy to tell, even if it's 6 or 7 volts and gotten a little ragged around the edges, it's still pretty easy to tell I've got a pulse there. So I've made that part of the job easier. I'm not decoding the actual signal on the wire. I'm just looking at the value of the bits to determine what the signal was. Remember, this is coded. Induced noise simply never gets decoded. I can wipe out data, but that's not the same thing. Okay, so we've solved that part of the problem. Attenuation and noise pickup have been addressed. That's why today, when you call overseas, it sounds, the audio quality is the same as if you call down the street. That's why. You don't have that buildup of noise. The flip side of this, remember we were looking at the fact that we wanted to move more, we had an increasing demand for voice channels, and it's really expensive to put in wire pairs. And so we were looking for ways to move more conversations across the media we'd already installed. If you look at the numbers, we've taken 24 DS0s, that's 24 individual conversations, and we've put them on an interface. A T1 interface consists of 2 pairs of wires. Okay? How many analog conversations can I move across 1 pair of wires? 1. So in other words, I've increased my carrying ability just with 1 level of multiplexing. I've increased my carrying ability by a factor of 12. Pretty impressive. If you look at the number of multiplex voice channels, and that's the carrying capacity gain you get as you go up this hierarchy. Now, again, you're looking at this thinking, what, 400 megabits, that's not that fast. My desktop runs faster than that. You're absolutely right, it does. Which is why this hierarchy is going away. You know what it does do real well? It's pretty darn immune to noise and all sorts of stuff that'll trash most high-speed digital carriers. Until you get to fiber to the house, you still have to deal with all this noise pickup and attenuation, data loss due to noise, data loss due to attenuation. Okay. Ultimately, we'll get enough infrastructure built out, and it's happening pretty fast, that I can deliver way more than this bandwidth anywhere I want. We're doing pretty well right now. LTE pushes an awful lot of data out to your phone. Anybody tried to get LTE outside the city limits? Around here? How much luck did you have getting LTE driving up the WK Parkway? Not much. It's because we don't have that infrastructure in place. Will we have it? Absolutely. And at that point, this class becomes superfluous because basically voice is then simply another application on a data network. It's pretty close now. The advantage of this is I can push these signals reliably pretty much anywhere. This infrastructure is built out, and that's why you still see it, and that's why you still run into it in industry. My guess is 5, maybe 6 years from now, we'll probably boil this class down to SIP, put it in as a module in 233, and that'll be it. Right now, you're still dealing with this. Okay. That's as far as I want to go today. What I want to talk about on Wednesday, there's some issues in doing this kind of stuff. For example, I've started taking square signals that decay real quickly on wire pairs. I'm running them through really noisy environments for a long way, and really bad things can happen to signals when you do that. So we're going to look at some of the protocol that's built in to help us detect when we have problems and we have data loss and stuff like that. We're not going to go way deep into it, but far enough that you can know how to configure one of these. And then we're going to look at this frame structure as a whole and look at how the signaling would work. That's my goal for this week, is to get you through the signaling on both analog and digital carriers. We're not going to be through, even when we get through with that part, we're not going to be through with T1 because it is still the most commonly deployed wide area net technology. Okay. You're going to run into T1, you're just not going to always use it as a voice carrier. It's a layer 2 data network. I can marry IP to that just as easily as I can marry it to Ethernet. Okay? And so we're going to take a look at the idea of using T1s as a data network in the wide area net. Okay? Okay? See you Wednesday.